FA2 further maths, cumulative distribution function. So last year we started looking at probability density functions, PDFs as they were called, which was to do with continuous random variables. Now we're going to extend slightly on this into what's called a cumulative distribution function, a CDF. Now a cumulative distribution function basically adds up the probability from a PDF up to a given amount. So a probability density function we looked at last year was written down as a lowercase f. A cumulative distribution function is defined as uppercase f. Now the difference is that when you're looking at the CDF, it's always a probability of less than a set value. So it's basically working out the probability from the very start, in other words, the zero, although it's not always a zero amount, the zero probability up to a set amount. Now, if you remember from last year, when we started looking at PDFs, we found things like the probability of something happening. And the way we found out the probability of something happening, an event occurring, we always worked out the area under the curve of a lowercase f. Now, because we're looking at a cumulative distribution function, which always works out the probability up to a set amount, it's all based on the area under the curve. And because it's based on the area of the curve, it's based on integration. So the integration is used to find the probability of a PDF, which is what I just mentioned. So therefore, to find our capital F, our cumulative distribution function, what we do is we work out the integration of, it says minus infinity, so that's basically the starting point, wherever your CDF starts from. It doesn't have to be zero, it could start in the negatives, it could start in the positives, it doesn't make any difference. So from before it, the probability will be zero. So once you've found out that starting position, up to any given point, all right, any given point x, you're integrating the PDF, the probability density function, within a certain value which we can call t. Okay, so what I'd like you to do is just have a think about what the graph of a capital F would look like for each of these continuous probability density functions. Okay, so these are your PDFs, these four graphs here. What would a CDF look like for these? So let me just explain slightly what you're doing then. So if you imagine that from the starting point, a CDF will definitely be zero because everything before that can't happen. There's nothing else is happening before this zero mark. Now once you get to this point, if you imagine you go from there to about 0.1, this probability starts to pick up. It starts to pick up relatively quickly, really, because it's up here about 0.4. Now, after that point, it starts to go down until by the time it gets to number 5, it's definitely nothing else is going to occur after that. So between 5 and 0 is where everything's going to occur. Your job is to think about what the graph of that would look like. Right? If you look at the area that's going from there to there. Okay, right, so I'll pause. If you know what I mean, by all means have a go at all three of them. If you're not too sure, maybe watch the first one as an example and then you can get on with the other three after it. Okay, so let's have a quick look at this first one, and then I'll give you an opportunity to pause again. So on this one here, we start off with quite a high probability to start with. So although it's at 0, because before it there's no area at all. In fact, if I just take a microscopic moment forwards, there's still hardly anything because it's a ridiculously thin rectangle or trapezium at that point. So it's going to be, as soon as I pass, it is going to start picking up, and it's going to pick up relatively quickly, because like this, and it's probably going to pick up until it reaches its maximum value. Now the maximum value of a probability density function, of course, the area underneath all of that is equal to 1. And once I get past 5, it's going to continue being 1. So if someone says, what's the probability to get less than 6? It's still equal to 1, because that's the same as 5. What's the probability to get less than 10? Still 1, because it's the same as less than 5, and so on. So my graph is going to start looking at that. It's going to go up higher and higher, higher, but when it gets down here, it starts to slow down. It starts to slow down because you've got less and less area, and you imagine you get close to 5, you're adding very small amounts to the area. And once you get to 5, you can carry that line on equal to 1. Okay, right, have a go with the other 3. And again, if you want to another look at the next one, by all means play it. Okay, so let's have a look at how you did with this one. So this time, once you start at 0, same as before, starts at 0. Before it is nothing's going to occur. Once you get past 0, your probability takes it's a lot slower this time. All right, it's not the probability between, let's say, 0 and 0.5 is very small. The area under that is very small. It starts to pick up more towards the end. Probability between 1.5 and 2 is quite big. So I'm looking at a graph that starts picking up the area small. So the probability below 1 is still relatively small. Probability between 1.5 is a bit bigger, and so on. So let's have a look how that looks on the graph. Starts small. In fact, it looks to me like it's almost identical to the previous one. Okay, they are very, very similar graphs. What does this look like then? And it goes from there, it will just be a straight line because past number 2 would be 1. And just so you can sort of understand why this has occurred, if you think about this graph here, that's a little bit like an x squared curve. Okay, that's like an x squared, a quadratic curve, like that. Obviously, it will carry on the other way and so on. Okay, but just this section here is like an x squared. Now, this is the integration of that function. So if I integrate that function, the x squared, you're going to get x cubed over 3. You're going to get x cubed. Now, this is part of an x cubed graph. Okay, that's what's happened there. It's the same reason as this one was a linear graph. And if you integrate something like x, it goes to x squared over 2, which is why you start to get some sort of quadratic graph just there. Okay, it's a bit upside down. It's an upside down graph, but that makes sense because it's a negative gradient. Right, so have a go at those two, see how you get on. And right, so let's see how you got on with this one. Now, this one's a bit different because it does something there. Then after that point, it does something else. Now this first bit is quite similar to that one, except for the fact it's a straight line. The second part is almost identical to this. So I'm expecting that sort of shape about halfway through. Now to start with, I'm probably expecting more of that shape. So this graph is going to go up, gets to the middle, and then starts to go like that. So it looks a bit like a cumulative function that you dealt with at school. Okay. Right, so then add to the final one. So let's see how far you got on the final one. So this straight line just here, so that would be, for example, y equals 3. So this graph of y equals 3, now if you integrate y equals 3, you know that you're going to get 3x. So it's going to go from a straight line to, sorry, a straight horizontal line to a straight linear function, 3x. So that straight line just there is going to go up. Once it hits this point, this graph that goes down just tails off, the same as that one and that one. Once you get to that point, it stays at number 1 forever then. So it always starts at 0, does a bit in the middle, always finishes at 1. And that's the same for all of these graphs, up to 0, off to 1, up to 0, straight line from 1. Okay, so well done if you managed to get any of those graphs. You do need to be able to transform from one to the other, okay, like these sorts of things here without equations. But generally speaking, you'll have an equation, so therefore you'll be able to work out the graph accurately. Right. Okay, so let's have a quick look at an example. So what I'd like you to do is just grab your notebooks and put this question into your notebooks, and we'll look at how to find a CDF from a given PDF, and also how to sketch the graph properly, and also find a probability. Okay, so once you've got it down in your notebooks, just restart the video. Okay, so let's have a quick look at that first question. So if I want to change to a CDF, I'm going to be using this formula just here that changes from a PDF to a CDF. Notice that I need to break this down into at least 2 sections. The reason for that is because we've got some functions that occur between 0 and 2, and then a different function from 2 to 3. And so because of that reason, I've need to make sure that when I'm using this formula, which helps us find the CDFs, I deal with one section at a time. So I'm looking at the 0 to 2 section just here. So my minus infinity is my starting point. In this case, it is starting at 0. So before 0, nothing occurs. No probability happens. 0 is when this function starts. And I look at up to only 2 because I don't want to deal with the 3/5 just yet. Okay, right, notice that you are dealing with some t value. And that t value is any value between 0 and 2. It's not an x, because the x value is your variable. You don't want to be putting that into it. What you're looking at is, well, it's a new variable. This variable t is some t value between 0 and 2. Okay, and to get the formula, we look at substituting x in at the top and the starting position, which is 0 at the bottom. Okay, so you could do the integration yourself. 3t squared over 20 dt, so that's just going to be increase the power to 3, put it underneath, 3's cancel out, so well done, t cubed over 20. You can put your x value in, take away your 0, so that's going to be x cubed over 20, take away 0 cubed over 20, which leaves us this value here as the start of our cumulative density function. And notice that if you differentiate that, you'll get back to this first point, just there. Okay, right, so the first part is dealt with. The first part's always the easiest part. Once you get past the first bit, then you're dealing with this 3/5. Now, the common mistake that people make is then using this function from where they think minus infinity is the start there too, but it's not. The minus infinity is always the starting position. So you'll notice that you're always starting, in this case, at x equals 0. Just beware, it's not always x equals 0. It depends on where your function starts to pick up a probability. So in this case, it's at the 0 mark. Right, so that means I'm looking for the cumulative density function from 0 up to 3 now. Now the issue is it contains this bit just here and a bit of this, okay, anywhere between 2 and 3. So what I need to do is write that down. So I know from going from 0 up to x, I'm not sure what the function is going to be because there's two different functions. But what I can definitely do is split this up. I can deal with 0 to 2 and I can deal with 2 to something else. Now the 0 to 2 is definitely going to all occur. So that bit just there is definitely going to be happening because I've passed that point and now I'm into this function just here. So my 3t squared over 20 goes from 0 to 2. I could figure out the probability of that part. That gets me to number 2, and then I'm some amount of, I don't know how much, into the 3/5, so somewhere between 2 and 3. Okay, this section you could probably calculate using your calculator. You could do it however you want, or you could just put the number 2 straight into there because that's what the x value would be. It's up to you. Okay, so this value here is going to be 8 over 20. So there we go, 8 over 20. This value just here comes from me integrating 3/5. So that will be 3t over 5, which is where that bit comes from. I can substitute the x into it. I can substitute the 2 into it to get that. And then once I've done both of those parts, I can then stick this together as a single fraction. So 2 minus 6 is minus 4. So 3x minus 4 over 5. Now what's a good idea just to check is that if you've got these right, they should link up. So for example, at 0, when I put 0 into there, I get 0. So it's definitely a starting point. At number 2, when I put it into here, I'm going to get 8 over 20. The start of this one should link up. So if I put number 2 in there, I'm going to get 3 times 2 is 6. 6 minus 4 is going to be 2. 2 over 5. Now 2 over 5 is exactly the same as 8 over 20. If you times top and bottom by 4, you would get 8 over 20. So these two definitely link up. So when that one finishes at 8/20, this one starts at 8/20, and then at the very end, when you get to 0, all right, so when we get to number 3, we should have finished all the probability, okay, because it's 0 everywhere else. So a final check could be, if I put number 3 into it, do I get 1? So 3 times 3 is 9, 9 minus 4 is 5, 5 over 5 is 1. So the whole thing links up. From 0, these two things link up, leading up to 1. Okay, and that's what this is saying. You can check your boundary points, 0, 2, 3, just to check whether it actually works. You'll soon know when you come to sketching your graph. Speaking of which, now we've got our cumulative density function, we can put this together. So there we go. We can say, right, to start with, from anything before 0 is going to equal 0. As it says there, all CDFs must start with the probability 0. Before that point, nothing can occur. So that's below 0, just there. Once you get to 0 and 2 in our CDF, it was this part just here which we integrated, and that was the x cubed over 20. That's the differentiation of that bit. Once we got to number 2 though, from the 2 to 3 category, was not just 3/5. Alright, it wasn't just 3x over 5. So if you look back at your previous bit of work, that included this, so therefore that's where this came from, 3x minus 4 over 5. Once you get to number 3, as you can see if you substitute in here, everything greater than 3 does stay at 1. So these all link up, so hopefully we'll see that when we draw our graph. Just take note of these two. All CDFs must start at 0. All CDFs must finish at 1. That's a subtle difference between the two things. This always has 0 otherwise, because anywhere else would be a probability 0, whereas this has a clear start and finish values. Not just that, just check out the started thing. PDF, CDF. Right, let's have a quick look at sketching the graph. Now we've got all these equations, what we can do is we can just draw sections, it's almost like a restricted domain of these graphs. Okay, so below 0, down here, nothing's happening. Boring, 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 up to 0. Once you get to 0, now you're following the x cubed over 20 graph. Now x cubed graph looks like this. It all goes up, does a turn in the middle, all right, has a stationary point in the middle, and then starts going like this. So past 0, that's what it looks like. Now it's 1/20th of it, so it's squashed down. Okay, but it's definitely still got that same shape. Also, we know its endpoint. All right, at number 2, it has an endpoint, which we know is going to be 8 over 20 or 2/5. So just there, that's where it's going to end. So I could sketch that part of the graph in. It's going to look like that. If you're not sure, feel free to just put a couple points in, 0.5, 1, 1.52. Just substitute them in, plot a couple of points, give yourself your nice curve. Okay, so certainly that first section we can put in, it's going to go up like that, finish at 0.4, all right, 2/5. Once it gets to that point, then this graph takes over. Now this graph, 3x minus 4 over 5, is a linear function. You can see that because it's 3/5 x, take away 4/5. So 3/5 is its gradient. Starting there, we know that already because we checked out what number 2 was. And we know it finishes at 1. So you really don't need to worry about gradients and intercepts and all that sort of stuff because we know it starts there. We know it finishes up here where 3 equals 1. So what we could just do is just join those two parts together. Okay, and there we go. I wasn't far off back there. There is the graph of my CDF. After that point, it's 1. It's always a good idea to just draw the little line just the end of your axes. And there we go. Okay, right. Let's have a look at why it's good to have a CDF. What's a CDF good for? Well, one of the good things about a CDF is it allows you to calculate probabilities very easily. So for example, in this case, if I want the probability when x is less than or equal to 2.6, if I was on a PDF there, I would have to work out the area between 0 and 2.6. I would have to think about which equation I'm going to use. It's a bit of a pain. But now you've got a CDF, all you need to say is, well, if I want 2.6, 2.6 is in here, excuse me, in here, 2.6 is in here, so all I need to do is substitute it into that formula. That's it. I don't need to worry about anything else before it. All I need to do is just put it straight into this bit. The same rules apply if it was greater than and all those sorts of things. You might have to do 1 minus, but the CDFs are very good for working out probabilities. Okay, and this is what this is saying here. So the probability that x is, because it's a less than or equal to, it could be less than, it's the same thing because it's a continuous function. So if I want the probability of less than, it is literally just put the x value in as 2.3. So that's what this is saying, put the 2.3 straight into this function because 2.6 lies in there. If it was 1.6, you would substitute in that bit. So find the probability when x is less than 2.6 equals, there we go, about 0.76. That's it. Don't need to do any more work. That is the probability that x is less than 2.6. Okay, so what I'd like you to do is, given that CDF, could you work out the PDF? What would the PDF look like? So you might want to pause, have a go yourselves. Doesn't matter if you get it wrong. Okay, so let's see what you did. So if this is a CDF, and you know how to get from a PDF, probability density function, to a cumulative distribution function, you have to integrate. So if you have to integrate to get from there to there, well, how would you get back, as I've mentioned already, is going to be differentiation. So you differentiate to get back, you integrate to get from a PDF to a CDF. And that's what we're going to be using here. You can use differentiation to find a PDF from a known CDF. So look at the subtle difference there. It's literally saying if you differentiate your capital F, you get your lowercase f. If you differentiate that function, you get that function. Okay, I pause it if you need more time on that. Right, so let's have a look what you should get then. Well, the 0 and the 1, the 0 and the 1 are constants. So I can just ignore those. They're both going to go to 0 for when I differentiate them. So those two aren't really going to cause a problem. It's these two bits in the middle that I need to worry about. Those two are the otherwise section. Right, x squared minus 4 over 16. I hope you can do that yourself. But if you can't, what I would say is, look, you can just rearrange it slightly. So for example, let's just get past that bit. There we go. So for example, if I took x squared minus 4 over 16, I could write it as x squared over 16 minus a quarter. So a 16th x squared is going to go to, bring the 2 to the front, decrease the power by 1, so therefore it's 2 over 16, which is an eighth. So it's x over 8. The minus a quarter part, when you differentiate that, will just cancel out. That doesn't make any difference. So what does that go to? It differentiates to x over 8. Same what I did with this. Might have spotted that one a bit easier. So if I've got 2x minus 5 over 4, I can write that as x over 2, 2x over 4, minus 5 over 4. Again, if I differentiate that, the x over 2 is just going to go to a half, and the minus 5 over 4 is going to cancel out. So there we go. I've got my PDF calculated from that CDF. Okay. So you now know how to go from a PDF, probability density function, to a cumulative distribution function. You know how to get from one to the other and potentially back again. So some of the other questions you might get asked if you already have a cumulative distribution function, or if you've already calculated a cumulative distribution function, one of the questions you might ask is about the median. And the reason why you get asked the median is because the median is all about a probability equaling 0.5. So it actually has a what's the probability of x is equal to 0.5. Now this question here could be rephrased any way they like. They could have just asked you what's the probability x is below a given value equals 0.45. But you need to be aware that if they talk about the median, then you're talking about how do you find the halfway point. And look at what you're talking here. If you're dealing with this, if I find the halfway point, that value x will be the median, because anything below it equals 0.45 and anything above it will equal 0.5. So that x will be smack bang in the middle. So how do I do it? Well, I need to figure out which of these functions I'm going to be just making equal to 0.5. Now the way you're going to do that is just first of all, just double check where the 0.5 will lie. And I could do that by just checking this mid value just here. So it doesn't matter which one you use. I'm going to use this one. Okay. I'm going to put number 4 into it. 2 times 4 is 8. 8 take away 5 is 3/4. All right, so that's a probability. Anything less than that function would have 3/4 of the probability under it. Now the probability here is 0.5. So that's definitely going to be below there. The median does not lie in that region because that starts at 0.75 and then goes up to 1. So that really is the upper part of the probability distribution function, probability density function. Whereas if you look at this bit here, if I put number 4 in, yes, I get 0.75, but the 0.5 will be somewhere in there. You just don't know whereabouts with this x. So now that I've figured out whereabouts the 0.5 is, okay, because that was 0.75, so it's definitely below it, I can make this equal to 0.5, okay? And now all I need to do is just do a bit of rearranging. Times it by 16 gets you 8. Take away, add 4 to it, gets us 12, and then square root. So that's where the square root of 12 comes from. Notice that x value is in between 2 and 4. It should be, which is why we can ignore the negative. Okay. Always be aware of thinking, well, I thought it was plus and minus. It would be plus and minus, but you're looking at the solution between 2 and 4. Okay. Doesn't have to be. It can actually be a negative if these were all in the negative section. All right, so just be wary of that. Right, so the median is about 3.46. If you put in 3.46 into there, that's where the half would come from. Now, for working out the median or working out equal to any probability is always the same. So if you had a question saying when is the probability 0.8, you would then check where is 0.8. Now, as I stated earlier on, if you put number 4 into here, you get 0.75. So 0.8 would actually be in that section. So you'd make that equal to 0.8 and then rearrange and find x. So it all depends on whereabouts the boundaries are. Okay. So cumulative can be used to work out the median. It can be used to work out any quartiles you like. It can work out any probability. You just got to figure out where it lies. So just a bit of a reminder, if they're asking you to find the lower quartile, that's when you're setting your F value to be quartile 1, which is 0.25. The median is a second quartile, right? Because that's halfway, 2/4 is a half. The upper quartile is quartile 3, so that's 3/4, that's why it's 0.75. But they could also ask you any probability, any percentile, and you just put whatever the percentile is over 100. So if you want the 10th, the top 10% or the bottom 10%, then you could put 10 into there. Well, the bottom 10% will put 10 in. Top 10% would be put 90 in there, 90 out of 100. Right, so I've sort of shown you how to sketch CDFs. I've shown you how to calculate CDFs from a PDF and potentially go backwards. But we've also looked at some basic questions you might get with it to do with probability and percentiles. What you guys need to do is practice both of these sections. Don't be lazy. Make sure you're practicing nearly all of the questions in each of those sections because you don't want to be missing out on some of the easier marks that come with PDFs and CDFs.